Good evening, everybody. As I promised earlier, I uploaded a video regarding units and dimensions. I think you people saw the video and got a sufficient knowledge to solve the problems. So today I want to explain a new chapter in the NEET. You will get exactly 3 to 4 questions in the new chapter also. So try to listen the chapter carefully and get good marks in upcoming NEET Re-NEET exam 2026 on June 21st. So the second chapter I want to explain is a semiconductors. I want to explain the second chapter, which is semiconductors. Very important chapter for semiconductors. Semiconductors, which is very important chapter, which is very important chapter for NEET at 2026 exam. So before starting the semiconductors, first I want to explain about the band theory. What is meant by a band theory? A small concept I want to explain about the band theory. So what is meant by the band theory? Means an isolated atom, an isolated atom, an isolated atom consists of a discrete energy levels, discrete energy levels, energy levels in which electrons will revolve. Electrons will revolve. Discrete energy levels in which electrons will revolve. If you take a solid, in a solid, there are much atoms. There are much atoms which are closely packed. Which are closely packed. So the energy levels of one atom, energy levels of one atom overlap with energy levels of neighboring atoms, energy levels of neighboring atoms, energy levels of neighboring atoms, there forms energy bands. There forms energy bands. So very important band theory. So there forms energy bands. So see, this is one atom. So these are the energy levels of one atom. Energy levels of one atom. So see a neighboring atom here. This is the neighboring atom in the solid. These are the energy levels of this neighboring atom. So these energy levels of neighboring atom, they will get overlap with the energy levels of these energy levels of neighboring atom, with which gets overlap with the energy levels of another atom. There, these energy levels, this is called energy band. So these energy levels will overlap and forms a band, that is called band theory, energy band. So energy levels will overlap and forms energy bands. So according to band theory, solids are classified into three. Solids. According to band theory, solids are classified into three. One is conductors. Second one is insulators. Third one is semiconductors. Third one is semiconductors. So in this, we will read about the semiconductors. So next slide I want to explain. First, what is meant by conductor? What is meant by the conductors? Conductors means, so generally every solid consists of bands. One is called valency band and another is called conduction band. This is, every solid consists of valency band and conduction band separated by some energy gap. This is a forbidden energy gap. A forbidden energy gap separated by a gap which is called a forbidden energy gap. So this is valency band and that is a conduction band. Every solid consists of every solid consists of valence band and conduction band. A conduction band, valency band and conduction band are separated by energy gap. Separated by energy gap. That energy gap is called energy gap. That energy gap is called a forbidden energy gap. So this is valency band, conduction band, forbidden energy gap. What happens in solid? Valency band and conduction band, valence band and conduction band will get overlap, and conduction band will get overlap, overlap. Forbidden energy gap is zero. There is no forbidden energy gap between valency band and conduction band. There is no forbidden energy gap between valency band and a conduction band. Now, insulators. Next one is insulators. What is meant by an insulator? There is a large forbidden energy gap. Large forbidden. There is a large forbidden energy gap. Nearly greater than 3 electron volts between valency band and conduction band. So now third one is a semiconductor. This is most important for us. Now, third one is a semiconductor. There is a small forbidden energy gap. There is a small forbidden energy gap between valency band and conduction band. So semiconductors are germanium silicon. Example, germanium silicon are a semiconductors. Germanium silicon are semiconductors. So forbidden energy gap in germanium 0.7 electron volt. A forbidden energy gap in silicon 1.1 electron volt. So according to band theory, solids are classified into conductors, insulators, and semiconductors. Now, semiconductors are two types. Semiconductors are two types. Semiconductors are two types. First one, semiconductors are two types. First one, intrinsic semiconductor. Intrinsic, because why I am telling the concepts? Because conceptual bits you will get in the examination. That's why it is must to know some concepts here. In one exam I saw, what is the forbidden energy gap in silicon they asked. What is the forbidden energy gap in germanium they asked. So there is a possibility, what is the forbidden energy gap in insulator? So like that they are asking, that's why I am teaching the concepts also here in this chapter. Intrinsic semiconductor means pure form of germanium silicon are called intrinsic semiconductor. Intrinsic semiconductor. Pure form of germanium silicon are called intrinsic semiconductors. A second one is extrinsic semiconductor. Extrinsic semiconductor. Second one. Impure form of germanium silicon are called extrinsic semiconductors. So what is the impurity? Impure form. Actually, adding of impurity to semiconductor is called doping. Adding of impurity to a semiconductor is called a doping. Why we have to dope the impurity? So conductivity of semiconductor increases, impurities, adding of impurity increases the conductivity of the semiconductor. So very important, adding impurity, to semiconductor, to germanium silicon, increases its conductivity, very, very important. That's why you have to dope. So adding of impurity to semiconductor is called doping. Adding of impurity increases the conductivity. Very, very important. So actually, germanium, silicon are tetravalent elements. Germanium, silicon are tetravalent elements. Germanium, silicon are tetravalent elements. That means valency 4. Valency 4 means silicon, if you take 14, its atomic number 1s2, 2s2, 2p6, 3s1. That means if you take the electronic configuration, this is 3s. Okay, 1s2, 2s2, 2p6, 3s2, 3p2, I think. 1 minute. 1s2, 2s2. 14 I should get, na? So 14 I should get. So 1s2, 2s2, 2p6, 3s2, 3p6, 3p2. Okay. 1s2, 2s2, 10, 12, and 1 minute, 3p6. So 3p2. 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s2, 3p. So if you take the higher orbit, third orbit, in this you have 2 electrons here, 3s, and here px, py, pz is there, p orbital. So only 1 and 1. So here vacancy is there here. This is a 3p. This is ground state. This is in ground state. In excited state, what happens? Excited state. In excited state, this electron in 3s, the electron in the 3s, one electron will occupy the 3pz. That means one is there already, another is there. Here this electron will occupy the p state. So that's why it is called valency 4. So extrinsic semiconductors, 2 types. Extrinsic semiconductor are 2 types. 2 types. P-type semiconductor, and N-type semiconductor. P-type semiconductor and N-type semiconductor, 2 types actually. Extrinsic semiconductors are 2 types. That means P-type semiconductor means a trivalent element you have to dope with tetravalent. N-type semiconductor means this is pentavalent element you have to dope. 5 valency, pentavalent. So 10 pentavalent element. Here it is trivalent element. Trivalent. So trivalent element doped with trivalent element doped with a p-type semiconductor doped with silicon or germanium, you will get the p-type semiconductor. And pentavalent element, you will get n-type semiconductor. That means, see here, this is 4 valency of germanium or silicon. 4 valency of germanium or silicon. Okay, 4 valency of germanium or silicon. If I doped this 4 valency with trivalent element, if I dope this 4 valency element with trivalent element like this, see here, this is the trivalent. What happens? Here, these will form the covalent bonds. These electrons will form the covalent bond. Here, for pairing of this electron, you will have a deficiency. This is called hole. Hole. So, deficiency of electron is called hole. Okay, this is p-type semiconductor. P-type semiconductor. That means germanium or silicon doped with gallium or indium. So if you doped with gallium or indium trivalent element, so you will get a p-type semiconductor. When silicon doped with gallium or indium, you will get a p-type. So these are called covalent bonds. So sharing of the electrons, covalent bonds. You will get the covalent bonds here, and a deficiency of the electron will be there. Deficiency of electron is called hole. Is called hole. Very, very important. Absence of electron is hole. Here, majority charge carriers are holes. Minority are electrons. This question is asking in the examination. Majority charge carriers. Majority charge carriers are holes here in p-type semiconductor. In p-type semiconductor, majority charge carriers are hole. So, if a pentavalent element, phosphorus, if pentavalent element phosphorus doped with, if pentavalent element doped with a silicon, n-type semiconductor may form. N-type semiconductor forms. So in examination, they are asking what is p-type semiconductor, what is n-type semiconductor. So n-type semiconductor forms. Here, same concept actually, what I want to explain here. So this is silicon, let it be. This is a silicon. So 4 valency. If you doped with a pentavalent element, that is phosphorus. This is silicon, this is phosphorus. So you will have a pentavalent element, 5 valency. See here, 5 valency. What happens? These will form covalent bonds. There forms covalent bonds. One excess electron is there. This is called excess electron. Excess electron is there here. So that's why majority charge carriers are electrons. Minority charge carriers are holes. Minority charge carriers are holes. Majority charge carriers are electrons. Minority charge carriers are holes. Very important. And one thing I want to tell, as a whole, P-type, N-type semiconductors are neutral. P-type and N-type semiconductors are neutral. P-type and N-type semiconductors are neutral as a whole. So this is very, 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 very important concept what I want to explain. Now, PN junction diode. What is meant by PN junction diode? PN junction diode. What is meant by a PN junction diode? Very, very important. So one question may get in the theory what I taught so far, and one question will get from this PN junction diode. So take germanium or silicon. Generally here, a silicon is more preferred than germanium because of its high thermal stability. Generally, we'll prefer the silicon than germanium because silicon has high thermal stability. One side doped with trivalent element, one side doped with pentavalent element. So this is the so-called junction is a PN junction diode. This is trivalent element is doped. Trivalent. Take germanium or silicon, one side doped with trivalent, another side is doped with a pentavalent. That means phosphorus. Pentavalent element. One side doped with trivalent and another side is doped with a pentavalent element. The so formed junction is PN junction diode. So here, these are the holes, majority charge carriers in P-type semiconductor. You can call it as holes. And here, these are the electrons. Electrons I denoted by dot, and holes I denoted by a circle. So this is a so-called PN junction diode. What happened now? Due to high concentration, due to high concentration of holes and electrons, electrons diffuses into p region. Electron diffuses into p region. Electron diffuses into p region, and holes diffuses into n region. Holes diffuses into n region due to high concentration into n region. Okay, due to n region. At junction, a layer free of charge will be developed. A layer free of charge will be developed. at the junction will be developed. This is called depletion layer. A depletion layer. Depletion layer. A layer which is called a depletion layer. And let it be D. Its value is 1 micrometer actually. So 10 power minus 6 meters nearly. A depletion layer. Now, what happens now? Due to immobile ions, due to immobile ions on on p side electrons and n side holes, a potential difference develop across the junction. A potential difference develops. A potential difference develops across the junction. A potential difference developed across the junction called a potential barrier. Across the junction called a potential barrier. So in the problems, these are asking about this potential barrier. In germanium, this potential barrier is 0.3 volts. In silicon, this potential barrier is 0.7 volts. So that means what I want to say here, because of immobile, so actually this is the applied potential. So this is the applied potential. Somehow let it be for forward bias or reverse bias. Here there is a depletion layer here. I told this is P type, this is N type. Here what I am telling is, so immobile ions are there here, electrons in the P region and holes in the N region. Because of these, you will have a potential barrier here. Potential barrier. That's why what I'm telling. Potential barrier. In germanium, if they mention the germanium means automatically you have to take 0.3 volts. If they mention the silicon diode means you have to take automatically 0.7 volts. There is no other alternative. If they give the values, okay. If they will not give the value also, you should remember the potential barrier in germanium and the potential barrier in the silicon. What is the net potential they will ask? Problems are there. So what is the net potential? 100%. This you should not get forgot. Net potential is nothing but applied potential minus potential barrier. That is the net potential across the diode. So this is applied potential. This is applied potential and that is the net potential. So we have so many problems based on that. When resistance is connected to this, what is the current flowing in the, like that they will ask. Question is there. See, I is equal to V by R, V minus VB by a resistance. So that's why current in the circuit, if a resistance is given in the circuit, what is the current flowing in the circuit? If they ask, the formula for current, you should not take this V. V minus VB you have to take for calculating the current. This type of problems are giving in the NEET examination. Very important. So the symbol of diode is in the circuit. This is a circuit symbol of diode. So like this, this is P regia, this is N regia. This is a circuit symbol of diode. In the circuit, the diode will be like this. Circuit symbol of diode. This is P side, this is N side, this is the circuit symbol of the diode. So very important concept. What I taught now, that is potential barrier and depletion layer. Because of these two, a strong electric field, a strong electric field, a strong electric field created across a junction. A strong electric field created across the junction. Across the junction, very important, junction, due to a depletion layer and potential barrier. So that strong electric field is nothing but potential barrier by a depletion layer. The average potential barrier of germanium silicon is 0.5 by 10 power minus 6. No doubt, a strong potential, a strong electric field is created across the junction 5 into 10 power 5 volt per meter. So average value of average potential barrier, it is 0.3 plus 0.7 by 2. That's why you will take as average potential barrier is 0.5. Very, 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 very important. Based on this formula, you have problems once again. You have problems once again here. Here there are two types of currents are there. One is a diffusion current. In exam, they are asking this also. A diffusion current and a drift current. A drift current. Diffusion current and a drift current. There are two types of currents are there here. They are asking in the examination. Diffusion means because of high concentration, electrons are, because of high concentration, you know that holes are diffusing towards the, because of high concentration, holes are diffusing towards the uh, N regia, and electrons are diffusing towards the P regia. There, a diffusion current will be there. The diffusion current is diffusion current 100% is from P regia to N regia, and the drift current is from N regia to P regia. So diffusion current from P side to N side, P side to N side, N side. This is the diffusion current. And the next one is a drift current actually. Okay, drift current which is from N side to P side. Diffusion current is N side to P side. So because of uh, diffusion of holes into N regia and because of diffusion of electrons into P regia, a current will be flown through the diode, that is a diffusion current P. Drift current means what happened now? Here the depletion layer is there now, that is electron hole pair. Diffusion current is nothing but at the junction, electrons and holes will combine. The electric field, what it will perform? The electric field performs a work that electrons it sent to N regia and holes will send to P regia. So there a current develop, that is called drift current. Strong electric field, strong electric field sent it will send the electrons to N regia and holes to P regia, and there a current will develop, that is called a drift current and a diffuse. In the examination, they are asking a theoretical bit, a drift current is from which side to which side, and a diffusion current from which side to which side they are asking actually. So very, very important. diffusion current and drift current. So ideal diode, resistance of an ideal diode is zero. Resistance of ideal diode is a zero. This is the resistance of the ideal diode. So I will stop the lesson up to here now. So in the next session, I will continue from this. So please read all the concepts what I taught so far and try to get good marks and please subscribe these videos so that it will be benefited for the needy people who are appearing for a re-NEET exam going to be held on June 21st. So I promised you I will complete all the important chapters which may get more and more questions and you will get the more and more marks. Thank you. Thank you once again. Thank you.